Fluid Mechanics 1 SEMM 2313. So for today, we would like to discuss about the flow in pipe. So when water comes out of a faucet, it has a certain velocity. The velocity can be calculated using the idea of Torricelli theorem. So I hope you understand how to get this equation. So it is start from a tank here. So and then we have a pipe, for example, at this one at here. So if we calculate using Bernoulli equation, so this is point number 1 and this is point number 2. So we could get that the velocity at 2 here, it is equal to square root of 2gh, where the h here is the distance from the outlet and the inlet here. So this is the h. So and then for sure, this is the common phenomenon. So the water will flow out from faucet, and so it will flow at certain velocity. So when the faucet is fitted with a short rubber hose, the water comes out with a velocity that is slightly less than the velocity of the water leaving the faucet. So this phenomenon is quite a common phenomenon. So for example, if you have a faucet here, okay, so and then you connect with a short rubber hose, so the water is still flow at certain velocity. So and then when a long rubber hose is used, there is a possibility that the water coming out will be slowed down. So this indicates there is a loss of energy in the flow. So this is also a common phenomenon. So I think you have experience of this. So it means that if we have a faucet here, so and then we connect with a long hose, water hose here, so you will find that the water that comes out from this hose is slower compared to the water that comes out from the faucet. So it is because the kinetic energy in the liquid here is actually used to overcome the friction along the rubber hose here. That's why the velocity at the outlet here is much slower compared to the velocity of water that comes out from this faucet here. Therefore, Bernoulli equation need to be modified. From previous chapter, Bernoulli equation written as this one. So this is the common Bernoulli equation that you know that in previous lesson we assumed that the energy at inlet is equal to energy at outlet. So we assume that the energy is constant along the streamline. So in this case, we need to modify a little bit this Bernoulli equation because we need to show the energy losses. So in this case, we assume that the flow is steady and uniform and there is no energy loss along the flow. In the situation where we need to take into account the loss of energy, the Bernoulli equation needs to be written like this. So we need to change the way we express the Bernoulli equation. So we write the Bernoulli equation at point number 1, which is the inlet. So it is equal to Bernoulli equation at the outlet here, and then we add an extra term here that we call as losses. So the idea is very simple. So for example, the energy at inlet is 10. So and then maybe the losses along the flow is 2. So means that the energy that reach the outlet point is actually 8. Because the total energy at inlet must be equal to the total energy at the outlet here. So energy loss can be divided into two main types, namely major losses and minor losses. Major losses are associated with frictional energy loss that is caused by the viscous effect of the fluid and roughness of the pipe wall. Major losses create a pressure drop along the pipe since the pressure must work to overcome the frictional resistance. So and then the second one is the minor losses. minor losses represent additional energy dissipation in the flow, usually caused by secondary flow induced by curvature or recirculation, the existence of parts in the pipe system, and the design of the pipe system itself. So there are two type of losses. One is major and one is minor losses. So major losses mean the losses that must occur in flow. So we cannot neglect that friction is there and certain portion of energy needs to overcome the friction all the time. So friction in fluid flow is actually not controllable, okay, and then for sure losses must occur. However, the second type of losses, we call it as minor losses. So minor losses is actually sometimes it is very small and it can be neglected. So minor losses is actually depends or caused by additional parts that we added into the pipe system. So and then we could expand the Bernoulli equation and we could write as this one. So we have the energy at inlet. So it is equal to energy at outlet plus the minor losses here and plus the major losses here and plus the minor losses here. Okay, we will discuss in detail about the major loss. As we know, previously we learned about the ideal flow. The velocity profile in ideal flow can be shown like this. So this is, I think you are all students familiar with this velocity profile. So why we could draw the velocity profile same like this one, because there is no slip condition. There is no slip condition phenomenon on the pipe wall. So means that the molecule at this wall is actually not stick on the wall. So the molecule here at the wall is actually move at the same speed with other molecule. So it is, we call it as ideal flow, because why this molecule can flow at certain velocity on the surface, because there are no resistance on this surface. So that's why we call this flow as an ideal flow, because in ideal condition there is no friction, but in real friction, in real situation, friction must be there. But the velocity profile in real flow is drawn like this. The phenomenon of no slip condition occurs and the maximum velocity occurs in the middle of the pipe. So why the velocity profile start from here? Because we have a molecule that stick very hard, so there is no slip condition. So slip condition means molecule could move. Because the friction is very high, the molecule is stay on the surface and the velocity is equal to 0. So and then the molecule will keep increasing and then it reach the maximum at the middle of the pipe. If your diameter pipe is very large, so maybe you will have a velocity distribution like this. So means at the center point here, so more area will flow with average velocity. So if your diameter is small, so maybe the velocity profile look like this one. So means that it has only the highest velocity only occur at the center. So if your diameter is very large, so maybe the velocity profile is increased at the starting point. So and then it will constant and then it will go to 0 like this one. The friction that occurs between the molecule and the pipe wall causes energy loss to occur in the fluid flow. The longer the pipe, the higher the energy loss due to friction. That's why we can observe the water coming out from the long rubber pipe is slow compared to the velocity of the water coming out directly from the faucet. So this is the equation to calculate the major loss. So we could calculate the major loss as F L over D V square over 2G. So the F here is the frictional factor. This is the dimensionless numbers showing how much the friction occur on that pipe. So, and then because major loss occur due to the resistance or friction on the pipe, so means that the L here is the length of the pipe and the D here is the diameter of the pipe. So for example, we have a pipe from here to here. So because resistance occur on this pipe surface, so means that we need to use the length of this pipe and the diameter of the pipe as a part of the parameter to measure the friction. So and then we have V square over 2G. So this V square over 2G is actually show the kinetic energy. And the velocity here, okay, the velocity here is the velocity of the fluid flowing in the pipe. So mean the velocity is actually the velocity inside the pipe. So the velocity of liquid moving inside that pipe. And then we know in fluid flow, we have two types of flow. One is laminar and one is turbulent. So to calculate the major loss occur at any condition, whether your flow is laminar or your flow is turbulent. So both type of flow actually could give you a resistance. However, the resistance amount, the magnitude, the value of the resistance is depend on the flow. So we need to determine whether it is laminar or turbulent. Because if the flow is laminar, we could calculate straight away the value of F, the friction factor, as 64 over Reynolds number. So this is the fixed equation for us to calculate the value of F. However, if the flow is turbulent flow, so we need to refer to Mudi chart, and it is dependent on the relative roughness value. So if the flow is turbulent, so we need to get the value of F from Mudi chart. So what is Mudi chart? So this is the example of Mudi chart. So if you see here, so we have the left hand side x-axis here, which show the friction factor. So we have an x-axis here shows the Reynolds number, and we have the right hand side y-axis shows the relative roughness. So the basic idea is we need to determine these two parameters first, the Reynolds number and the relative roughness. Then, okay, for example, we have a line here. So this line is actually shows you the value of relative roughness. First, you need to determine what is your relative roughness. So the relative roughness is the epsilon over D. So in some textbook, they will write as E over D. So the E here, or the epsilon here, is the surface roughness of the inner surface of the pipe. So the unit is in millimeter or in micron. So and then the diameter here. So the diameter here is the diameter of the inner diameter of pipe. So because we want to make a ratio E between D, so please make sure that you divide them with same units. So if the E here is in micron meter or micron, so you need to divide by diameter also in micrometer, because we could cancel out the units. So and then the value of epsilon over D or E over D will become dimensionless. So and then if you see here, so there is a number here. For example, this is 0.0004. So means that this is the line for relative roughness 0.0004. So and then we could calculate the Reynolds number. Reynolds number equation, Re is rho Vd over mu. So we could calculate this one because we know the diameter and the velocity. So and then, for example, we have a 10 to the power of 6, and this is 10 to the power of 7, this is 10 to the power of 5. Let's say we have a 5 times 10 to the power of 5, so it is between here. Okay, so this is 5, so times 10 to the power of 5. So and then you draw a vertical line here until it intersects with the relative roughness. So this is the intersect point. So and then from the intersect point, we could calculate the value of f here by drawing the straight line to the left here, and this value is the value of the friction factor. So for example, here it is equal to f, it is equal to 0.017 maybe. So after you get the value of f, you just come back into this equation. You substitute the value of f here, 0.0017. So and then you could calculate the amount of major loss. So the unit for the major loss is in meter. Okay, so why? Because in Bernoulli equation, we could see that all this unit is in meter. So for sure, the major loss here is in meter, and also the minor loss is in meter. So what is the meaning of meter here? So it means that if that energy, the loss energy, try to push up, try to bring water upward, so it could bring until a few meters. So this is the meaning of meter, to represent the strength of the energy that loss in the system. Okay, I just repeat again here. So because this is very important, I hope all students could check their friction factor, from the Mudi chart. So first, you need to do the relative roughness. So and then, for example, you get relative roughness between these 2 points, for example. So what you need to do is you need to draw your imaginary line first. So for example, you are going to get a value between 0.0002 and 0.0004. So and then you need to draw your imaginary line like this in the middle, in between those 2 lines. So and then you find the 5 times 10 to the 5, so it is around here. So you draw a straight line here, and then you only take the intersect line here. So this is your friction factors value. So means that in this calculation, you need to calculate very, very detailed. So and then the roughness can be found in the table here. So I hope you could very careful. This is the type of pipe. So for example, we have riveted steel, we have concrete, wood, and so on. And this is the roughness in feet, British unit, and this is the value in E, in millimeter. So please make sure that if you want to use SI unit, you take the value of roughness on the right side here. Okay, example. The galvanized iron pipe normally has a surface roughness of 0.15 millimeter. Diameter of galvanized iron pipe is 0.375 meter. So first we need to divide these two value to get the relative roughness. So we divide 0.15 millimeters with 375 millimeters. So please make sure the unit is the same, and then we get it is 0.0004. So and then we assume that the Reynolds number is 2.5 times 10 to the power of 5. So we could calculate the Reynolds number by using this equation. So and then we could get the friction factor is 0.018. Okay, so for example, we have the 0.04 here. So this is the line. So and then we have 2.5 times 10 to the power of 5. So it is here. So the intersect point, okay, you just bring to the left hand side here. So it is around this value. So we could so you need to find the exact value on the left hand side y-axis. So it is equal to 0.018 here. So the friction factor is dimensionless. So dimensionless means there are no unit for that parameter. So this is a few points to ponder. Determine the value of the Reynolds number first, because laminar and turbulent flow have different methods of determining the value of the friction factor. So point number one is please check the Reynolds number first. The second one is make sure you know the type of pipe material and pipe diameter. This will give a different relative roughness value. Okay, why? Because Reynolds number alone is not capable to determine the friction factor. It must have the surface roughness. So the surface roughness is actually depends. So because, for example, we have the Reynolds number is rho VD over mu. So the diameter may be the same, but the material is different. So the material, when the material is different, so the value of surface roughness, the relative roughness might be different. So different line here will give you different value of friction factor. So and then the third one is determine that the diameter of the pipe. Even if the pipe type is the same pipe material, different diameter will give different Reynolds number value. So this is the idea of the major loss. I hope a student could know how to find the friction factor from the Mudi chart.